Okay, this is a quick screen recording to show how superposition would work to solve this simple Kirchhoff's voltage law loop. What we have here is a voltage source V1, a voltage source V2. I'll define I1, the current flowing in, I2, the current flowing in from the second source, and I3. What we ideally want to know is how much current is flowing inside R2, and potentially what the voltage is at Vx, this node. So how do we do this with superposition rather than using Kirchhoff's voltage law loops? Here's a start. We're going to have to short circuit V2, and then what we will do, we will work out the current in R2, the center resistor, I3, okay, knowing the value of I1, finding originally I1. So there's a couple of steps inside doing this. So you're familiar with this circuit now. Let's redraw it because we've got that short circuit. So we now have this circuit. This is R1, R2, R3. I'm going to redefine the values at all. The currents, I2 has now changed direction. I1 is my signal in V1. Okay, so my circuit has changed considerably, and it's an awful lot easier. I've got the parallel components of R3 and R2, and I've got a series resistance R1. So I should easily be able to write out that I1 is equal to V1 over R1 plus R2, R3 over R2 plus R3. Okay? If I now plug in some numbers for that one, I can calculate I1. I have 10 volts divided by the resistance. R1 is 1000 ohms, R2 is 3000 ohms, and R3 is 2000 ohms. The sum total of 2 and 3 is 5000 ohms. Okay, let's plug in some numbers into the calculator and see what we get for I1. Well, I've made that 4.5 milliamps. Okay, so there's my current I1 proportional to V1. I now need to deploy a current divider rule. Let's just look here. I1 is flowing into this node, and it flows out as I3, and it flows out as I2. Okay, so I3 is equal to I1, and in the current divider rule we choose the opposite resistance, that's R3, over the sum of the two, R2 plus R3. Okay, let's plug in some numbers for that one. So we now get I3 is equal to 4.5 e minus 3, exponential form just to keep it tidy, and here we have R3, that's 2000 ohms, divided by 2000 plus 3000. Okay, and that gives me the current 1.82 milliamps. Okay, smaller than the 4.5 and what I would expect. So now what I've done, this value here is the current flowing in R2, the middle resistor, as a function of the first voltage source, not the second voltage source. Okay, so that's drawing a line. That's the first part of superposition. So I've worked out what this energy or this supply does inside R2, this middle resistor. Now I'm going to work out what happens in the other resistor, or the other angle. So now I've got a different circuit, so I'll redraw it. Okay, so this is now my V2, and this is a 12 volt source. This is 2000 ohms, 3000 ohms, R2, R3, R1, 1000 ohms. This is now I2, so the current's changed direction. I3 is the same direction, and I1 has changed direction. Okay, exactly what we did before, we can now calculate I2. So I2 is equal to V2 divided by R2 plus R3, R1, R3 plus R1. Plug in some numbers. We've got 12 volts divided by 2000 plus 3000 times 1000 over the sum total 4000. Okay, plug in the numbers for that one, and what do we actually get? We get 4.4 milliamps. Okay, so that's the total current flowing in I2 proportional to V2. We now got a current divider. The current is flowing into this junction, and it flows out through I2 and R2. I1 and I3. So that's R1 and R3 in this particular design. Okay, so let's write out my current divider loop. I3 is equal to I2. Okay, so it's the current flowing in that we just calculated, and this time it's R1 over R1 plus R3. Let's plug in the numbers. That's 4.4 E minus 3 times, this time, 1000 ohms over 1000 ohms plus 3000 ohms. Okay, quick calculation for that one says that's 1.1 milliamps. So we've now got two currents. Okay, these are the two currents that are important. This current here, 1.82 milliamps, and this current here, 1.1 milliamps. So let's just make a note of exactly what's happening. I3 with respect to V1, okay, gives me 1.82 milliamps. I3 with respect to V2 gives me 1.1 milliamps. They're both in the same direction in the way the currents have flown. Therefore, I3 in the superposition is simply 1.82 milliamps plus 1.1 milliamp, 2.92 milliamps. Okay, effectively that. Oh, I didn't mean to draw that out. What am I doing? Equals 2.92. Okay, that is my current that's flowing. Just to work out, Vx, or the voltage across R3, is equal to 2.92 E minus 3 times 3000 ohms, which in this case is 8.76 volts. Okay, so if I just check that with a circuit simulation, I've got one here. What have we got? 2.909, so 2.91. I've got some quick rounding errors on my calculation, but that's fine. And now these currents will not show up, okay? These currents are not showing up in my simulation because I've only calculated this one. Because I calculated the energy coming from V1 flowing in the R2 resistance, and I calculated the energy flowing from that one. But at no time have I actually calculated how the currents would vary at the top here. So those are different calculations. But what I have managed to find, and quite clearly I found this value, and I found the voltage across that resistor. So superposition, an awful lot simpler than, say, doing a Kirchhoff's voltage law and lots of equations. Nice and simple, and a quick calculation. All we needed to know here was how to rearrange the circuit, parallel resistance, series resistance, and of course current divider rule.